Wijnen. We're going to talk about, of course, he's going to talk about the Mars analog missions, simulating human robotics mission on the red planet. As you all already heard, we hear in points. It's a little bit of analog missions. We have two analog mission centers here in Poland, and of course, we also take missions in Utah. And several other places. So we are very interested in the topic of the human robotic missions, because as we all know, there won't be Mars exploration and of course other planets exploration without robots. So let me just tell you a little bit about today's lecturer. So Dr. Wijnen completed his bachelor's degree in mathematics and physics and astronomy at the University of Utrecht, the Netherlands, followed by a research internship at the Universidad da Valparaíso, Chile, a master's degree with distinction, and a PhD in astrophysics. He has been captain in the Royal Netherlands Air Force Reserve and engages in projects on space situation awareness for the Dutch Space Security Center. So more things that we have in common, of course. He works as instrumentation coordinator for NOVA, Netherlands Research School of Astronomy, coordinating the many instrumentation projects in which the Dutch astronomical community is involved. Dr. Thomas holds a PhD, scuba diving, and a parachute license, and it's fluent in Dutch and English. So we're gonna hear, of course, today's lecture in English. Dr. Wijnen, I'm very sorry for the pronunciation of your second name. It's quite impossible to remember, but thank you very much for your being here with us. The stage goes to you.
Thank you. You can just call me Thomas, and thank you for the lovely introduction, Evelina. Yeah, so it's an honor to talk to you about the analog missions that we do at the Austrian Space Forum, for which I've been an analog astronaut since 2019 now, so 6 years. And yeah, so at the Austrian Space Forum, we mostly focus on future Mars missions. So why Mars? Yeah, so Mars was once like planet Earth. It had an atmosphere, it had liquid water probably. So most of the ingredients for life as we know it. So if we want to look for biosignatures, if there was life elsewhere in the solar system, then Mars is a very good candidate. But now conditions are much more harsh than they used to be, because the atmosphere has been eroded, and like there's only 1% left, and it's a CO2 atmosphere, contrary to the atmosphere we have on the Earth. It's extremely cold. The average temperature is minus 60 degrees, and it can be down to 130 degrees at nights. So these are all difficulties that we would have to overcome if humans would ever set foot on Mars. Also to keep into account, there's no magnetic field. Mars doesn't have a magnetic field that would protect us from radiation. Yeah, you're constantly being bombarded also because there's such a thin atmosphere by micrometeorites. So there is still some water in the form of ice on Mars near the poles. So that's a very also a promising region to look, but also other regions where we have already proven by rovers and other missions that there has been liquid water, and that are old water seabeds or riverbeds. But Mars does not have plate tectonics as we know it, for example. So everything scales differently. So here you see a picture of Olympus Mons, for example, taken from space. You can really see this from space. The biggest mountain on Mars, which is the size of France, basically. So when we think of Mars nowadays, then this is the images that have been returned to us by various missions. It's a dry, cold, radiation-exposed deserts. So that if we would ever go there, that's quite, yeah, we wouldn't be able to survive on the surface without wearing a spacesuit, as you all know, of course. So, as I said, Mars once had all the ingredients for life. It was habitable, but the question is if it ever was really inhabited. And here you see the Korolev impact crater. So this is a cold trap with permanent water ice. Again, an interesting location to look to. And I would say so for the first time in our history, we are able to tackle such question, to see if Mars ever was inhabited and go there and investigate this. But as soon as we formulated that the scientific questions, if life has ever arose on Mars, we need to think about which method do we use? How can we investigate this? What are the minimal ingredients? What are we going to look for? Biomarker molecules, for example, that indicate something ever lived there. And also, how can we do this in such a way that we do not contaminate what we're looking for, such that the biomarkers that we would find, that we don't bring them from Earth. As I said, we've had various missions, robotic missions already to Mars. Here you see a selfie by the Perseverance rover. This is basically the size of a car, which was launched almost 5 years ago and successfully landed on Mars 4 years ago. And this is collecting samples to be picked up by future missions and then return to Earth. So it leaves both sample tubes on board of the rover, and it also leaves them at various places on the surface. So this is what we do already in terms of robotic missions and returning samples to Earth. Of course, this is quite an investment, and being able to research this in situ by humans that are much more versatile than a robot is something that can happen in the near future. This is also really a technology driver, because building something that is able to drive around on Mars is quite an endeavor and a challenge. As you see here, everything has to happen in sterile environments because we don't want to have any forward contamination, as we call it. So don't want to contaminate Mars, and that we actually bring the biomarkers or biosignatures that we're looking for. One other, I think, a very important part of the Perseverance mission or rover is that it brought a small helicopter, and that was really a technology demonstrator, because before that it was not certain if the Mars atmosphere would be thick enough such that a helicopter could fly there. It's called Ingenuity. But this is just under 2 kilograms, and it was a very successful technology demonstrator. So it made 72 flights in nearly 3 years, over 2 hours of cumulative flight time, and it traveled more than 17,000 kilometers in the horizontal direction at a maximum height of 24 meters. And this concept that could be also be used on a future mission to collect the samples that have been left by the Perseverance rover and then be returned robotically. Well, so over the past decades, in the last 65 years, there have been a lot of robotic missions to Mars, and you see an overview here, from flybys in the upper arc to orbiters, landers, and rovers by many different countries and states. But going to Mars is not easy. With the average success rate is about 55% for overall missions, But if we only look at the subset of rovers and landers, it's still that same success percentage, although we have been better at it in the recent years. So most mission failures happened decades ago. But of course, it's a huge challenge and it's difficult. So that's why it's very important that we prepare for this here on Earth, particularly when it involves humans. And that is what we do as the Austrian Space Forum. We've had several missions already. And last year in Armenia, we conducted our 14th analog Mars mission in March to April, a 4-week mission that included 15 experiments from various sciences, so robotics and human factors, but also geosciences. And I will give examples of what those experiments were. It's also already setting up such an analog mission here on Earth is a really an investment. So over 250 people and researchers and volunteers were involved, representing more than 26 nations. And what you see here on this picture is the habitat that was particularly, I hope you can see my cursor, that was built for this particular mission in an environment. Again, this is a desert-like environment that is as similar as we can get on Earth. This was a view basically with our back to the habitats, and then we could see Mount Ararat, which is a sacred mountain in the region. It was a beautiful view. It is said, believed that Moses got the 10 amendments on the mountain. But as I said, we chose this region because it shows a lot of similarities with the environment on Mars. So here you see the slope, for example, the steepness of the slopes that indicate comparable geomorphic processes and a uniform geological influence that shape these features. So the top is Mars and the bottom is Earth. And you can always recognize this from the atmosphere, which is blue on Earth. And on Mars, there's basically no atmosphere, a very thin one. So here again on the left, we see rugged characteristics of Earth geological features, and on the right on Mars. And again, you see potential similarities in geological processes that form these environments. So on Earth, we're looking for an environment that is as close to Mars as we can get. And the final one I have here is again on the left is Mars, on the right is in Armenia. That these futures suggest the comparable underlying geological processes. Of course, what is a huge difference here in these pictures is there's vegetation in the Armenian desert, and there's none on Mars. So as I said, in order to be able to survive on Mars and withstand the cold temperatures and radiation, micrometeorite bombardment, we basically need to wear a spacesuit for one, a spacesuit simulator. And at the Austrian Space Forum, we've developed our AUDA-X spacesuit simulator, and it simulates the main characteristics of an actual spacesuit that you would have to wear on Mars. And so the whole suit weighs about 50 kilograms. When it was developed some 15 years ago, that was considered the equivalent weight of a suit on Mars. So an actual suit suitable to wear on Mars would be around 130 kilograms. So this would be about 38% of that, which is the gravitational equivalent of gravity on Mars. I guess with the current technology, we can reduce the weight a bit, and it would be very convenient because walking around in a 50-kilogram spacesuit is quite exhausting. It is unpressurized, so an actual suit on Mars would be pressurized. Our suit is not pressurized, but to mimic that aspect, we wear so pressurized would basically be like this Michelin guy. And you would have to exert all the movement that you do with your legs and your arms would have to be exerted against this pressure. But instead of pressurizing the suit, we use an exoskeleton on our legs and on our arms. And that mimics the same pressure we would experience if the suit would be pressurized. We have a custom-built onboard data handling system. So many all the telemetry data that is taken from the suit, temperature, CO2 levels, oxygen levels, that is being collected and sent through a central location. We have a heads-up display. And also for this suit, the outer layers are optimized for planetary protection, as I said, to protect from radiation and impact from micrometeorites. This suit carries a battery, so if it's fully charged, we can go somewhere between 4 to 8 hours of field operations, go outside in this suit. And as I already said, it has a broadband telemetry, so collecting all the relevant data and setting it to a central location. Yeah, what you see here, some aspects that are all related to this suit. So here you see my former colleague Kartik Kumar, where the exoskeleton is being put on his legs in this case. And here you see our director, Gernot Grömer, that also already has the exoskeleton on his legs. We wear a headset inside the suit. So once the helmet is closed, and we have vents that continuously provide a flow of fresh air that produces noise. And also when the helmet is closed, you're completely closed off the outside world. You cannot hear anything. So we really rely on communication via the headset. During our analog missions for communication with the suit, we use a Wi-Fi setup. What you see here is a Wi-Fi testing. This is the Wi-Fi antenna to communicate over longer distances and also send out the telemetry. We've done a cryo test with this actual suit down to minus 110 degrees. So the suit also has heating pads on the torso to keep the astronaut warm at these extreme temperatures. Of course, this was in a very localized ice lab. But we've tested the suit down to these extreme temperatures. Other extreme tests we've done is with 6 megavolt Tesla coils. So the suit basically is a Faraday cage. So this is the suit that we use for the mission. Years of development and experience have gone into this, and it's continuously being improved. Other aspects that are necessary in preparation for the mission are, of course, the host country providing the environment and the habitat to perform the actual mission. So here you see 2 years ago already a delegation from the Austrian Space Forum. So our director, Gernot Grömer, and Reinhard Tustos, board member of the Austrian Space Forum, together with Mer Mirapyan, he's a member of the Armenian Aerospace Agency, signing the cooperation agreement for our Amity 24 mission in Armenia that would be conducted a year later. So once this agreement is signed, then we can really start with the preparations for the mission. And we do this in various ways. So Before we actually go to Armenia with all the experiments, the equipments, and the suit, we have dress rehearsals in Austria, so several weekends in which everybody gets up to speed with all the procedures again. Here you see a nice picture of our ops console. So this is at the dress rehearsal, but during the actual mission, these computers are positioned inside the habitat. And this is where the analog astronauts that remain in the habitat stay in contact with the suit. So this is our Annika, my analog astronaut colleague. So here she's communicating with an analog astronaut that is in the suit. There was also a lot of media coverage. Before we start donning the suit, which takes about an hour and a half, 2 hours at the beginning of the mission. Of course, we want to do a lot of checks to make sure everything works. So you see my colleague Simone, who's checking the comm connections. We have various support teams that set up the local Wi-Fi infrastructure. So we're in Armenia, we're in the middle of the desert. So we really have to make our own infrastructure, and that also includes Wi-Fi to be able to communicate from the habitat to these suits, even when they're traversing on quads several kilometers away. So we need to send up a Wi-Fi network that has extensive coverage. As I said, we don't do this alone. So we have our what we call our GHOST, the Ground Operations and Support Team, of which you see a beautiful picture here during one of the dress rehearsals. So they provide support on site, so in Armenia. So they are not isolated in the actual habitat, but they prepare for the mission, setting up the habitat and the experiments. But once the mission actually starts, they're invisible. Hence the name Ghost has a double meaning to it. In order not to break the isolation protocol that we have during the mission. Here you see a picture of the crew. So our commander Annika Melis from Germany, Robert Wild, a deputy commander from Austria, Inigo from Spain, Carmen. Sorry, that was Siri. Carmen from Germany and Simone from Italy. So we're a crew of 6. The habitat was also suitable for 6-person crew. We usually conduct our missions with a 6-person crew. Maybe it's also nice to know. So the 4 of us here in the center, we're from the same class of 2019. And Carmen and Inigo are already from the class of 2015. So they've been an analog astronaut for 10 years now for the Austrian Space Forum. So as far as we're aware, the Austrian Space Forum is the only organization that maintains a continuous group of active analog astronauts. So then we go to Armenia. We set up everything. There are 2 containers that are being brought there that carry all the experiments that we do and all the other technological infrastructure that we need. It takes us a week to unpack everything and install everything. And then the mission that we call that the bridgehead phase. And then after a week of the bridgehead phase, we actually have the mission start ceremony, of which you see a nice picture here. Again, there was a lot of press coverage. And here you see Guyana, who was our local heroine. She arranged a lot of things there. So once the mission starts, the crew of us, we are the 6 of us in the habitat in isolation. And this is the typical Mars simulation infrastructure that we use. So we have a crew inside the habitat that is performing several experiments. And we have a mission support center that was located in Vienna, in Austria, and we communicate with a 10-minute delay. Due to the huge difference between Mars and Earth and the speed of light that is limited, information needs time to travel between the two planets. On average, the time delay would be about 20 minutes between Earth and Mars. But we know from experience with previous missions that 10 minutes simulates this aspect as well, but we get more science done. But there's not a lot of difference between implementing a 10 or 20-minute timeline. And we communicate via text messages, so via chat. And so the Mission Support Center, they are in contact with the actual experiment team. So these are experiments that have been proposed and suggested by various universities and research institutes. And there's a lot of things that they do actually at the Mission Support Center. So let me first show that to you. So that would be Earth. And here you see a picture of during the last mission in Armenia. And you see various positions here. We have the flight director that is in charge, overall responsible for the overall mission operations. This is the EarthCom, so that actually does the communication, direct communication with the analog astronauts in the habitat. Human factors, taking care of our mental well-being, both of the crew and also all the other people involved. So also in the Mission Support Center and the GHOST support team. The BME, the biomedical engineer, so they also, with a 10-minute delay, they get all the medical data. So we also wear an ECG, for example. And they keep an eye on our physical well-being. And they have the authority to give a no-go or no-go for an extravehicular activity. So for the analog astronauts to go out of the habitat in the spacesuits and perform experiments. And there are some other positions here, contacts and procedures that have contact with the experiment teams, for example, and make sure we have the most updated procedures. And this mission support center is actually supported by various backroom teams, so to say. The flight control team, for example, that help in analyzing data, preparing decisions in almost real time. And this picture illustrates the work that flight planning does. So they create a schedule of field activities. So here column, so here it would be, each row would be an analog astronaut. And you see very detailed schedules per day, very similar to what is used on the International Space Station, for example. And these can also be updated on a daily basis based on input that has been provided by us, the crew, or the experiment teams. But they also need to take into account safety aspects, route planning, if we're traversing, walking, or by quad outside, weather forecasts, or individual needs of scientists or crew members. So that is flight planning. That's one of the backroom teams that supports the Mission Support Center. Here we see the remote science support. That's mostly interested in the scientific data that is collected by the field crew, and they analyze this data very quickly. They stay also in contact with the research teams. They provide suggestions for the flight planning. Yeah, that's it. Oh yeah, and what's very nice to see here, actually, we see, where's my mouse? Yeah, here. The remote science supports team also had made a 3D VR rendering of the habitat in its environment. So even on Earth, in Austria and Vienna, they could get a feel of the environment we were in Armenia. Well, here you see a picture of the habitat near sunset. So on the right here is the airlock where we would go in and out with the spacesuits, and we had dedicated areas. You cannot see it here behind the glasses for donning and doffing. So putting on and taking off the spacesuit. Operations, those were the consoles that are in constant contact with the suits once they're outside. An experiment lab, exercise area, and kitchen, sleeping quarters to the further back. And even at the very end, there was an inflatable tent that carried one of the experiments called HOR3 Space. And this was also present at previous missions of the Austrian Space Forum. And the idea is here that almost semi-autonomously plants or editable plants can be grown. So we only have to set it up by spreading out the seeds and filling the water supply. And other than that, this whole machine with trays works autonomously and cultivates the seeds to make them grow, and we can then eat the vegetables that come out of this. As I mentioned, exercise is also very important. So for this particular mission, there was rowing equipment in the habitat. We also have one of our sponsors was an easy motion skin. So with actual vibrations, it stimulates various muscle groups to intensify the workout. And actually, this suit has also been used on board the ISS by ESA astronaut Matthias Maurer. Here you see Carmen and Inigo during one of the EVAs, so extravehicular activities. That's what we call it when the two AAs go out in the AUDA space suits. Yeah, that is a very important part of the mission. This is actually how we started as the ÖVF, where we focused on spacesuit developments in terms of requirements and procedures, how to work with such a spacesuit. And this is a nice movie. It does not have any sound, but here you can see that wearing this spacesuit takes more time. So even such a simple act as Inigo is doing here, opening a Ziploc bag or finding something in a suitcase, wearing 3 layers of gloves. So you also miss some dexterity. So everything takes more time while you're carrying a 45, 50 kilogram spacesuit. So this takes a lot of energy as well. I think, oh yeah, you also see a hammer here. This is we typically use this to collect rock samples, but also as a reference of size when we collect geological samples and take pictures. And of course, we also, for safety aspects, as would be the case on Mars, we always conduct EVAs in pairs. So never alone, but always the two of us. And as I said, so the ghost team, they're not visible here, not to us, but they are on site. Also people that are medically trained to provide assistance if something goes wrong, but that's just for our safety because any interference would be breaking simulation. Well, so what we do during these missions, we also do experiments where we investigate human-robotic interaction. So here you see one of several rovers that was present during this mission in Armenia. This is called the IROX rover. It is controlled by the analog astronaut, which is carrying the remote here. It can film. This records the environment. So, for example, when we were collecting rock samples, there's a camera in front. We position the rover such that it would film us collecting the rock samples. It also carried this particular rover also carried tooling to take geological samples. And here it has a box with a laptop and equipment to collect data from another experiment, which is called Farsight. So we were wearing sensors on our leg, one of our legs and one of our arms, and on our torso and on our head, and it was tracking the motion of our body. So you can see here how that then is turned into a computer animation. We also had sensors that tracked basically the exertion and fatigue of our muscles. So this would provide very valuable input for spacesuit design, but also planning and EVA planning experiments. I think this was one of the most exciting experiments that we did. Here you see me with one of the experiments that we did inside the habitat. So we had experience both inside and outside the habitat. We had a lot of questionnaires about our mental well-being, so psychological experiments. This one was called Staying Alive. Also very nice experiment where we had a presumable photobioreactor, which would then responsible be for our air revitalization, so the fresh air in our habitat, which was not actually the case, but the part of the experiment was that it was a very a life-saving component, so we have to keep it always up and running. And then we would have to perform several maintenance or troubleshooting procedures, either with the help of AI or without the help of AI, and then see how that would improve on procedures, for example, for future Mars missions, and also investigating the psychological impact on us, on the analog astronaut. Another picture here of an analog astronaut here taking geological samples. So we also create, for example, extended tools, because as you can imagine, doing a squat with 50 kilograms is quite exerting. So it helps if we have a tooling that makes things easier. And for this exam, for this called the GEOS experiment, we call it. That's all about developing procedures and training analog astronauts and astronauts how to take samples, and how can we train people that not have a geological background to take the best samples, and also do this in such a way that we do not contaminate Mars. If we look back at the moon, the missions to the moon, the Apollo missions, then in the end, the best samples have been collected by the only geologist, Harrison Schmitt, that was there on the last Apollo missions, Apollo 17. So good geological training is very important. Again, here is a very nice impression of how also the Ghost support team sometimes performed experiments with the rovers that did not require interaction with the analog astronauts in the suit. And here again, I have another movie. So this is a rover, Charlie rover, that is supposed to launch ultra-wideband transmitters as a projectile, not very far. but then that transmits its position, and it helps in mapping the environment. And what you also see here rotating is a laser scanning that also maps the environment. But in this video, you don't see anything happen, and that is part of also a real mission. Not everything goes as planned, and then we need to adjust. And that is why we do this. We want to fail fast and fail cheap, and here on Earth, any mistake is not deadly or life-threatening, while on Mars it would be. So that's why we conduct these analog missions. So this rover is to map the environment. We also had another experiment, Alex, that had radio antennas, basically, that we would position because on the moon or on Mars, there's no GPS. So perhaps with very simple radio antennas, we can use that for accurate localization of the AAs and experiments on Mars. So once we've collected the geological rock samples, there was another experiments in which we, as analog astronauts, were trained to prepare a thin section, so a cross section of a sample that would then be able to investigate that under a microscope and do spectroscopy on it. So basically, we'd have to cut a section from a rock sample and then polish it to about 100 micron thick thin section. And this is the whole setup that was provided for us to do that. This is a very nice example of human-robotic interaction. It's called the MEROP experiment. So here, from inside the habitat, the analog astronauts operate a rover that is outside. So we have a live camera feed on the laptop from the rover. We have a joystick to operate the rover. What you see here on Inigo's left hand is a device that rotates with the orientation of the rover. So if it's on a slope or slightly tilted, pivoted, then this device rotates along. So you get a feel of on how steep the slope is that the rover is on. And here for this experiment, Inigo is not wearing, but here's you cannot really see, but there's a glove that you can wear on your other hand, and that vibrates if the rover, the wheels lose traction. So this is an experiment where with or without what we call haptic feedback, we would get additional information from teleoperating a rover that is outside the habitat. And this is then the actual rover that we controlled from inside the habitat called sample. But this particular rover can also drive autonomously. So that's also an experiment that was done with this rover. Can it work semi-autonomously in this environment and find its way around the habitat? So there was a nice glance of all the experience we did during our Armenia mission. As I said earlier, this is the view from our habitat where the sun is setting behind Mount Ararat. After our mission, at the end of our mission, which was very successful in a sense. We had a science workshop end of last year where the scientists presented their first results, and they're very promising. You can find more information on our website. And this is, of course, a wonderful quote, and I don't know who it's attributed to, but I guess if you also want to get involved in analog missions, there are various ways to do that. Via the Astronomy Space Forum, as I've just been talking, you can always get in contact about joining for future missions. But there's also one other thing I would like to highlight here. So we're part of a new analog Mars station that's being built in Portugal. So 4 countries are involved: Portugal, Austria, France, and Greece. At least they received the funding. That will also be used for future Mars Moon analog missions. Also holding up to a 6-person crew for 2-week-long missions. And the operations will start this year. And it also has a mission support facility nearby, so also that you can simulate communication with Earth. Here you see a nice schematical drawing of the station layout. So it's similar in a sense to what we had in Armenia. So the airlock, this is the donning and doffing area, so where you could put on the suits, spaces for medical equipment and experiments, command stations where you can stay in contact with the suits, and the mission support center, and let's say the quarters, sleeping quarters, and the social area, and for hygiene, just to give you an idea. So this is an EU-funded project. There will be 2 student missions already planned in the coming 2 years, but it's part of a bigger educational program for schools. So we also have some physical kits that are handed out to schools that they can use in the classrooms, and we hope to reach a large audience. These are the project consortium partners. I will give you the slides afterwards. I'll put in this information so you have this. But I guess very important here, it's open for missions from halfway this year and onwards. And it will also participate in the world's biggest analog mission that you may or may not have heard of. So in October, I think it's actually October of this year, there's the world's biggest analog that involves 12 habitats around the world that are involved there. So basically mimicking that already there are several habitats on Mars that have to communicate among each other and with Earth. But I guess the most important message for you all listening is that the station is open for research and student activities starting this summer, and that teams can suggest missions similar to a model that you may know from Lunaris in Poland, or MDRS. And their organizations and the people in the organization behind this have a lot of experience in analog missions. And one other thing I'd like to pinpoint, so ESA has just built a beautiful Luna facility in Cologne. And it's actually very complementary to that facility because that has an inside area of 700 square meter of lunar regolith simulant. While here we have a huge 30,000 square meters open field site. So there you can mimic more all the traverse aspects of a mission to Mars. And both facilities have very experienced teams behind them. So if you want to know more about this, you can contact our director, Gernot Grummer. And thank you very much for attention, and I'm open to your questions.
Wonderful. Thank you so much. I just wanted to add that Dr. Grummer was one of our guests. I think it was about 2 or 3 months ago. It was also a unique lecture. And before we start, the questions, I have one question. You talked about that huge analog missions that will include 12 places. Did I hear right that there will be a Polish one also?
I don't know off the top, but then I would expect then that Lunaris would be involved, and maybe I can quickly check. But I remember that a couple of months ago I tried to get a list of the actual habitats that are involved, but I couldn't find it. But let me see if I can. Yeah, Lunaris is also on the list. Yes.
Oh, wonderful.
Yeah.
Nice to know. Okay, so are there any questions? Perhaps some from the floor. If not, please write your questions on chat and I will read them out loud. Hmm. Right. It's one from Mikołaj Karawecki from Polska.
Okay, because
Okay, no, start.
yes, Natalia, I can.
Start.
I can. Yes, very short. Okay. Thank you for a very interesting presentation. It's very interesting for me. And I have question about spacesuit. Maybe I didn't understand, but how is a solution of breathing? How you breathe in this spacesuit? It is a pump from outside, like in Utah, I remember, but or air condition. Can you explain me?
Yeah, it's a very good question. In the meantime, I'm searching the slide. Yeah, it's a very good question. So I didn't say this very explicitly, but we're in a sense we're a voluntary organization that depend also on partnerships and sponsors. So we don't have the extended budget that ESA and NASA have. So with the means that we have, we try to do the best that we could. So building an actual spacesuit that is a closed loop system, that is beyond our budget, unfortunately. But that also, if we would do that, that also means that lead developing times and such take much longer. While our approach is more of also a bit of what Elon Musk did in the beginning of SpaceX, fail quick, fail cheap, and learn fast. So in terms of fresh air, what we have is we have two inlet fans that suck in the fresh air from the outside, and we also have two outlet fans that then blow out the air that we breathe out, basically. So we have a continuous replenishment of fresh air inside the spacesuit. And the same is true indeed for the habitat. Again, that would be very costly to set up a self habitat that would be self-containing. So also there we can just take in fresh air from the outside. I don't think, well, not at least involved in the world's biggest analog mission. There's a real closed log system like there is on the board of the ISS.
Rather circulation system, yes, and from outside, yes, it is.
Yeah, so it's circulation, and we get fresh air from continuous fresh air from outside.
Outside, yes.
That's the short answer.
Okay.
Yeah.
Thank you very much.
Okay, so there won't be any type of MOXIE in your habitat.
Any kind of what? Sorry.
MOXIE, it's an instrument that flew to Mars and.
Sorry, MOXIE that was on the Perseverance rover.
Exactly.
Well, so so there could absolutely be an experiment like that inside our family, but that would have to be in a very contained, closed environment, so on a very small scale. Yeah, but not inside the habitat. We did actually, I didn't show any pictures of it, but we did have an experiment, another one, that monitored air quality and other things inside the habitat. So so we do have scientific experiments that are related to this.
All right. So let me read out loud the question from Mikołaj Karawecki from Polsa, Polish Space Agency. Do I understand correctly from the Habitat's windows at the Staying Alive experiment that your habitat is not a closed loop environment in terms of air, water, power, and life supports?
Yeah. So I had read the question already in the chat, so I answered it while I was answering the same question basically about the spacesuit. So it's the same concept for the habitat and the spacesuit. So indeed, they're not closed loop systems because at this stage that is too costly. And I also see a question about the technology that we use for 3D rendering of the habitat.
Exactly.
I think they used information from Google Maps and other. So and I don't know the actual sources they have, but before we go somewhere for a mission, we have all these backrooms teams and a remote science support team that look already in the area, what areas of interest are, and they get various maps of ground composition from different sources. And I think they use that to create this 3D rendering. So I'm quite sure there wasn't any person on site in Armenia that did a 3D scanning of the surroundings.
Right. And one from our colleague, Fatina, what kind of navigation have you used in the autonomous rovers?
That's a good question. So on Mars, of course, there's no GPS. So that's why these rovers, one rover, they map the environment, and then that can be provided as input for the other rovers. So what we, for example, didn't have during this mission, but had during a previous mission in Israel, we also had the drones that basically scanned and mapped the environment. And you can use that also. But to be honest, I'm not sure it was semi-autonomous. So that is then experiments that we as an AA are not directly involved in. So it's not completely autonomous. And perhaps they cheated a bit for some experiments using GPS, assuming there would be a similar localization infrastructure available on Mars.
Wonderful. Are there any more questions from the floor? Does it sound like? So there are no questions on chat. So Dr. Thomas, it was wonderful to hear all those things. I'm sure we learned a lot, especially that here in Subaki Pan, we make the type of technology. So there's more to know and more to do for us. Thank you very much. And I hope to see you again.
Yeah, thank you very much. It was my pleasure. And indeed, contributing with experiments is also a very good way of getting involved with the Austrian space for our missions. Yeah, but of course also at Lunaris, MDRS, and the Alkeva Analog Research Station. Thank you very much for all your attention, and have a great day.